Good afternoon, everyone. My name is Youpeng Zhao from the University of Science and Technology of China. I am honored to have the opportunity to introduce our work in Mahjong AI on behalf of our team. Here is the outline of my presentation. It consists of 4 parts. First, I will briefly review the background of Chinese standard Mahjong. After that, I will talk about the related work in Mahjong AI. Then I will introduce our method in detail and show the experimental results. Mahjong is a 4-player imperfect information game that originated in China more than 3,000 years ago. Mahjong requires the players to analyze the potential combinations of winning tiles according to the tiles at hand at each stage and estimate how many steps are needed from the current state to the final state. Obviously, it is a dynamic and complex decision process. Therefore, it is challenging to train an expert-level bot. It requires knowledge from different fields such as planning, game theory, heuristic search, MCTS, opponent modeling, and machine learning. Several methods are proposed to handle this problem. First is a role-based method. It will try to win as fast as possible. However, this method ignores opponent's tactics and has low defensive capabilities. Another mainstream is supervisor learning, where the bot will simulate human experts' tactics. However, supervisor learning requires a large amount of data, and the bot tends to lack overall view of the whole game, as it just responds to the current state. Recently, the technique of self-play plus reinforcement learning is also applied to this problem. It allows AI to learn by itself from zero, but this method requires a significant amount of computing resources. We are considering the limited computing resources. We adopt supervised learning to solve this problem. Here is a chart of our method. We extract states and actions that we need from human player game datasets and use the information to train our model. And in practical applications, we extract the states from raw data, which is generated from game core. And then we use the network to predict the corresponding actions. As for the definition of state, we refer to the work of MIC and SRA's suffix and do matrix modeling of the tiles. Based on their work, we made the following adjustments. Firstly, we changed the size of tensor from 1 times 34 to 4 times 9 in order to enhance the perception of winning hands like mixed shifted pawns and mixed triple choke, which are the most common winning hands in human games. What's more, we also reduce the number of channels of the tensor. Specifically, our state tensor has 145 channels, including private hand tiles, exposed mild of 4 players, exposed tiles in discard area, and the remaining unknown tiles. Where both the action for the action codes, we divide all actions of Mahjong amounting to 235 actions. And the 63 concrete conditions of chill are shown in the right charts. You can see them. And also, we adopt ResNet as the main architecture of our model due to its powerful representation capability. We build each block with a 3x3 convolutional layer, BN layer, and a ReLU activating layer. And we build a natural network with different depths to learn the mapping from state to action. And finally, I want to talk about the data processing. We get human player matrix datasets provided by BootZone, containing about 500,000 games. This is the link of our data source. And after getting the data, we first delete the records with error. For example, some records have the winning hands, but the points is lower than 8 points. So this game is error. And we extract the winners pairs of states and actions from each game. At last, we apply the data augmentation considering the symmetrical characteristic of Mahjong. We exchange the three suits, that is, bamboos, characters, and dots. Because if we just change these three suits, the record of game is also right. And in the experiment, we find that about 400,000 games, there's only 1,000 games is wrong after this way of data augmentation. And then we have the second way of data augmentation, that is, we can exchange number 1 and 9, 2 and 8, 3 and 7 and 4 and 6. In these two ways, we can get more data for training. Here are our experimental results. We adjust the depth of the network and the way of data augmentation. From the results, we can find that data augmentation can greatly boost the performance of our bots, while deeper networks have little effect. Where on December 28th, our bot with a ResNet 18 architecture ranked top in the ranking list of the community on the BootZone. In conclusion, we build a Mahjong AI with a method of imitation learning and make use of data augmentation to raise the diversity of data. And finally, we gain a fine result. That's all. Thank you for your listening.